An invisible force controls the ultimate fate of the cosmos. This is the mystery of dark energy, a power so profound it accelerates the expansion of the entire universe, yet remains completely hidden from direct view. By the end of this journey, you will understand how scientists are mapping the unseen geometry of this cosmic architect. We will explore how a discovery from the late 1990s shattered our understanding of physics and why Einstein's biggest mistake might be the key to it all. How do you begin to chart something you cannot see? And what does its hidden structure reveal about our final destiny? What does it mean to live in a universe shaped mostly by forces we are only beginning to perceive? The late 1990s delivered a cosmic shockwave that fundamentally rewrote the rules of the universe. Two rival teams of astronomers were engaged in a monumental task, meticulously measuring the faint light from exploding stars billions of light years away. They were using a specific kind of stellar explosion, a Type 1, a supernova, which has a remarkably predictable brightness. This makes them perfect cosmic mile markers or standard candles. By comparing how bright these supernovae actually were to how dim they appeared from Earth, the scientists could calculate precise distances across the cosmos. Their goal was to measure how much the universe's expansion had slowed over billions of years, pulled back by the relentless grip of gravity. The expectation was simple. The universe had been expanding since the Big Bang, and gravity, the great attractor, should have been putting on the brakes. But the data told a different story, a story that made no sense. The distant supernovae were fainter than they should have been, meaning they were farther away than anyone had predicted. The expansion of the universe was not slowing down. It was speeding up. Imagine the sheer disbelief of throwing a ball straight up into the sky, expecting it to fall back to Earth, only to watch it vanish into the heavens at an ever-increasing velocity. This was the scale of the paradox. Something was overpowering gravity itself, pushing galaxies apart with a mysterious, repulsive force. This discovery was so profound it earned the teams the Nobel Prize in Physics in 2011. It forced cosmology to confront a new and dominant component of the universe, an energy inherent to the fabric of space that drives it apart. We now call this force dark energy. But to truly grasp what this means, we must travel back in time to a theoretical seed planted by the most famous scientist of all, a concept he once called his greatest blunder. Einstein's so-called greatest blunder was in fact a stroke of profound intuition. While constructing his theory of general relativity, he faced a problem. His beautiful equations described a dynamic universe, one that should either be expanding or contracting under the influence of gravity. Yet, the scientific consensus of the early 20th century insisted the cosmos was eternal and static. To force his theory to match this prevailing view, Einstein introduced a fudge factor, a mathematical term he called the cosmological constant. Represented by the Greek letter lambda, this constant was a kind of anti-gravity, a repulsive force woven into the very fabric of space that would precisely balance gravity's pull, creating a stable, unchanging universe. It was an elegant fix, but it was built on a flawed premise. Just over a decade later, Edwin Hubble's observations of receding galaxies proved the universe was not static at all, but rapidly expanding. With the need for his balancing act gone, Einstein famously dismissed the cosmological constant as his biggest mistake. For decades, it was relegated to a footnote in the history of physics, a cautionary tale about bending theory to fit belief. The cosmic irony, of course, is breathtaking. The discovery of accelerating expansion in the late 1990s did not just challenge our understanding of gravity. It demanded the existence of a repulsive force acting on cosmic scales. The simplest mathematical description for that force, the one that fits most cleanly into the equations, is none other than Einstein's discarded cosmological constant. Lambda was back not as a mistake but as a potential master key. This revival points to a staggering idea that empty space is not truly empty. The vacuum of space itself possesses a faint, intrinsic energy. Think of it not as a void, but as a seething sea of quantum activity, where particles flicker in and out of existence. This quantum foam imbues every cubic centimeter of nothingness with a tiny, persistent push. Across the vast emptiness between galaxies, this tiny effect adds up to a cosmic shove powerful enough to stretch the universe itself. So, did Einstein accidentally predict dark energy a century ago? The cosmological constant provides an elegant, simple framework, a single number that defines the strength of dark energy, but its very simplicity raises new and deeper questions. Is the energy of the vacuum truly constant for all time, or could it change, perhaps evolving as the universe ages? The geometry of dark energy might be far more complex than a single number can capture, hinting at a dynamic force with a story yet to be told. Einstein's rubber sheet is a powerful image, but it has a crucial limitation. The sheet represents space at a single moment in time. To understand dark energy, we must think of that sheet as dynamic, as a movie instead of a photograph. Every massive object, from a planet to a galaxy cluster, creates a depression in this four-dimensional fabric. Objects orbit each other not because of a mysterious pull, but because they are following the curved paths, the geodesics, within these cosmic dimples. This is the elegant picture painted by general relativity, but dark energy introduces a new director to this cosmic film. It does not create another dimple on the sheet. Instead, it commands the entire sheet to stretch, causing the dimples themselves to move farther apart. The space between galaxies is not simply emptiness being crossed, it is actively growing. This is why the universe's expansion is so counterintuitive. Galaxies are not flying away from each other through space, they are being carried apart by the stretching of spacetime itself. The rate of this stretching, and whether it accelerates or decelerates, is determined by the geometry of the universe, a geometry shaped by the total amount of mass and energy within it. Think of it like trying to determine the final shape of a rising loaf of bread by studying the dough. The ingredients, the density of the dough, dictate whether it will rise slowly, rapidly, or even collapse. Dark energy is the most potent ingredient in our cosmic recipe, and its properties dictate the ultimate geometry of everything. To measure this, we need more than a single snapshot. We need a map of the universe in 3 dimensions across billions of years. This is where cosmology turns from theoretical elegance into a monumental feat of observation, using the universe itself as a laboratory. Mapping the cosmos in 3 dimensions requires a new kind of telescope, one that can capture not just a beautiful image, but a precise cosmic address for millions of galaxies. This is the work of projects like the Sloan Digital Sky Survey. Imagine a telescope that does not simply stare at one patch of sky, but systematically scans great swaths of the heavens, night after night. Instead of a single photographic plate, it uses a specialized metal plate drilled with hundreds of tiny holes. Each hole is positioned to align perfectly with a pre-identified galaxy. Into these holes, astronomers plug optical fibers, each one acting as a light pipe that channels the specific glow of a single, distant galaxy to a waiting spectrograph. This instrument is the key. It breaks the light from each galaxy into its constituent colors, its spectrum. By measuring how much that spectrum has been stretched toward the red end of the light spectrum, a phenomenon called redshift. Astronomers can calculate the galaxy's distance. The greater the redshift, the faster the galaxy is moving away from us and the farther away it is. With this data, each galaxy is no longer just a speck of light. It becomes a point in a three-dimensional map with coordinates right ascension, declination, and distance. After years of painstaking observation, these individual points begin to coalesce into a pattern, a structure of breathtaking scale and complexity. The universe reveals itself not as a random scattering of stars, but as a vast cosmic web. Gigantic clusters of galaxies, each containing thousands of island universes, form dense nodes. These nodes are connected by long, thread-like filaments of galaxies, weaving through the cosmos, and between these structures lie the voids, immense regions of near emptiness that can span hundreds of millions of light years. This web is the large-scale structure of the universe, and its geometry holds profound secrets. The pattern is a fossil, an imprint from the very earliest moments after the Big Bang. Tiny quantum fluctuations stretched to cosmic proportions by a period of hyperinflation served as the seeds for all structure. For billions of years, gravity acted as the master sculptor, pulling matter into these denser regions, carving out the voids and weaving the filaments. But dark energy is the other artist at work. As the universe ages, dark energy's influence grows, and it begins to oppose gravity's gathering power. It acts as a counterforce, making it harder for new structures to form and effectively freezing the growth of the cosmic web. By measuring the exact sizes of the voids and the clustering strength of the filaments at different cosmic epochs, scientists can take the measure of dark energy itself. A stronger, more repulsive dark energy would create larger voids and a more diffuse web. A weaker dark energy would allow gravity to build an even denser, more clotted structure. These grand maps are therefore more than just charts. They are a history book and a laboratory rolled into one, allowing us to read the story of the cosmic struggle between attraction and repulsion written across the sky. This cosmic web, a tapestry woven by gravity, holds a hidden pattern within its threads. Etched into the distribution of galaxies is a faint echo from the universe's fiery birth, a frozen sound wave that serves as one of our most precise cosmic measuring tapes. This is the story of Baryon acoustic oscillations. In the first few 100,000 years after the Big Bang, the universe was a seething, opaque soup of particles and light. In this dense plasma, gravity tried to pull matter together into clumps, while the intense pressure of radiation pushed it back out. This created a tug of war, generating vast spherical pressure waves that rippled outward through the primordial fog, much like sound waves moving through air. These were the Baryon acoustic oscillations ringing across the infant cosmos. Then, a pivotal event occurred, known as recombination. The universe expanded and cooled enough for electrons to combine with protons, forming the first neutral atoms. In that moment, the cosmic fog cleared. Light which had been trapped could finally travel freely, and we see that released light today as the cosmic microwave background. But something else happened at that instant. The pressure waves, which relied on the push and pull between matter and radiation, suddenly lost their driving force. They froze in place, leaving a permanent, spherical imprint in the distribution of matter. Imagine a single pebble dropped into a pond, creating a circular ripple that expands outward. Now imagine that the pond instantly freezes solid, preserving that ripple forever. This is what happened on a cosmic scale. Each region of slightly higher density in the early universe created such a frozen ripple. The result is a characteristic scale, a preferred distance. Galaxies are more likely to form at a specific distance from each other, corresponding to the radius of that ancient sound wave. This distance, about 500 million light-years across, becomes a standard ruler etched into the fabric of the cosmos. The Baryon Oscillation Spectroscopic Survey, known as BOSS, was designed to find this ruler. By meticulously mapping the three-dimensional positions of over 1 million galaxies, the survey revealed a subtle statistical preference for galaxies to be separated by this specific distance. It is not that you look at the map and see perfect circles, but by analyzing the clustering of millions of galaxies, the signal emerges with stunning clarity. The true power of this standard ruler lies in its constancy. Its true physical size is known from the physics of the early universe, but as we look out across billions of light-years, its apparent size in the sky changes. Not because the ruler itself shrinks or grows, but because the geometry of the space between us and the ruler is stretching. By measuring how the apparent size of this cosmic ruler changes at different epochs, astronomers can measure the expansion history of the universe with extraordinary precision. It is like having a series of yardsticks placed at different distances down a long hallway, and watching how the perspective on each yardstick changes to reveal the exact properties of the hallway itself. The BOSS measurements confirmed the accelerating expansion driven by dark energy, providing a completely independent and powerful check on the supernova results. This frozen sound wave gives us a direct read on the geometric evolution of the universe, a fundamental test that any theory of dark energy must pass. While Baryon acoustic oscillations give us a ruler etched in space, another technique maps the cosmos by watching how its mass warps the very path of light itself. This method returns to a core prediction of Einstein's general relativity, that gravity is the curvature of spacetime. A massive object like a galaxy cluster does not just sit in space, it bends the space around it. When light from a more distant galaxy travels through this warped region, its path is subtly bent, like a car driving over a curved stretch of road. The distant galaxy's image can be stretched and distorted. Most of the time, this effect is incredibly faint, a phenomenon known as weak gravitational lensing. Individual galaxies are not turned into dramatic arcs, but their shapes are minutely altered, stretched by fractions of a percent as their light journeys to us through the cosmic web. To see this, you need an incredibly sharp and stable eye on the sky. The Dark Energy Survey, or DES, provided exactly that. Using a 570-megapixel camera mounted on a telescope in Chile, DES spent 6 years peering into deep patches of the universe, cataloging the shapes of hundreds of millions of galaxies. The challenge is immense, as a galaxy's intrinsic shape is already irregular. The key is in the statistics. While any single distortion is negligible across a vast field of galaxies, the subtle, coherent twists imposed by the intervening dark matter reveal a pattern. Imagine looking down on a forest through a gently warped sheet of glass. You would not see any single tree perfectly bent, but across the entire canopy, a slight directional smearing would become apparent. DES was measuring this cosmic smearing by analyzing how the shapes of distant galaxies were systematically distorted. Scientists could trace the distribution of mass between us and them, most of which is invisible dark matter. This created a three-dimensional mass map of the universe's large-scale structure. But why does this mass map tell us about dark energy? It is all about the growth of structure over time. Gravity wants to pull matter together, making the cosmic web more pronounced as the universe ages. Dark energy, with its repulsive push, acts against this gravitational collapse. It effectively puts the brakes on the formation of new giant clusters and filaments. A universe dominated by a strong dark energy would have a weaker, more diffuse cosmic web than one where gravity reigns supreme. The weak lensing signal from DES measures the clumpiness of matter, the amplitude of the cosmic web. By comparing this clumpiness at different distances, and therefore different cosmic times, cosmologists can measure how the growth of structure has been suppressed throughout the history of the universe. It provides a direct, independent read on the strength and nature of dark energy's influence. The true power emerges when this weak lensing map is combined with the standard ruler of Baryon acoustic oscillations and the cosmic mile markers of supernova. Each probe examines a different consequence of dark energy, the expansion history, the geometry, and the growth of structure. When these independent lines of evidence all point to the same conclusion, the case becomes undeniable. They are not just seeing an effect, they are triangulating on a cause, building a robust, multi-faceted portrait of the force that shapes our cosmic destiny. These faint temperature ripples are the primordial blueprint for everything we see today. Each slightly warmer patch, a region of marginally higher density, would eventually become a gravitational well, pulling in more and more matter over billions of years to form the galaxy clusters and vast filaments of the cosmic web. Each cooler spot would evolve into one of the immense voids. The CMB is not just a baby picture, it is a detailed forecast. But to read that forecast, scientists must decode the precise statistical patterns in this cosmic static. This is where dark energy enters the story, not as a visible actor in the infant universe, but as a ghost in the machine of the equations. The Planck satellite, with its incredibly sensitive instruments, measured the size and distribution of these hot and cold spots with unprecedented accuracy. The geometry of these patterns is a direct reflection of the universe's total content at that very early time. The data tells us the universe is geometrically flat, which means the total density of matter and energy is precisely tuned to a critical value. Planck gave us an incredibly precise inventory of the universe at 380,000 years old. It measured the amount of ordinary matter, the amount of dark matter, and the total energy density. But when we add up these components from the baby picture, they only account for about 1/3 of the critical density needed for a flat universe. There is a huge deficit. This is the profound clue. The universe is flat, so the total density must equal 100%. The early universe inventory is missing about 2/3 of the required energy. This missing component must be something that was negligible in the universe's youth, when matter was densely packed and its gravitational pull was overwhelming. But as the universe expanded and matter thinned out, this dormant component would have emerged to dominate the cosmic energy budget. That component is dark energy. The CMB does not see dark energy directly, but it leaves a glaring, empty space for it in the accounting books of the cosmos. It sets the starting gun for the race between gravity and repulsion. When we take the initial conditions precisely measured by Planck and run the cosmic simulation forward in time, using the laws of physics, the only way to arrive at the universe we see today, with its specific rate of acceleration and its frozen cosmic web, is to include a dark energy component that makes up about 68% of everything. The baby picture and the adult universe are in perfect agreement, but only if this mysterious, repulsive force is writing the final chapters of the story. This single number, W, the equation of state, is the fundamental key that unlocks the nature of dark energy. It is a deceptively simple ratio, comparing the pressure dark energy exerts to its energy density. Think of it like this: you can describe a gas by its pressure and density, and the relationship between them tells you how it will behave. Dark energy is no different. For the cosmological constant, Einstein's revived idea, this ratio is locked at a value of -1. This specific number has a profound consequence. It means that as the universe expands and the volume of space increases, the energy density of dark energy remains constant. Picture a magical gas that does not thin out as it fills a larger container. This constant density is what leads to the accelerating expansion we observe, a steady and unceasing push. But what if dark energy is not so simple? What if W is not exactly -1? This is where the true mystery deepens. If W were slightly greater than -1, say -0.9, it would suggest that dark energy is not a static property of the vacuum but a dynamic field, perhaps similar to the one that drove inflation in the universe's first moments. This quintessence field could slowly evolve over cosmic time, its strength fading or ebbing, changing the ultimate fate of the cosmos. The acceleration might not continue forever. It could one day slow or even reverse. The other possibility is even more dramatic. If W is less than -1, we enter the realm of phantom energy. In this scenario, the energy density of dark energy would not stay constant. It would actually increase as the universe expands. This would lead to an acceleration that feeds upon itself, growing exponentially more violent. The result could be a cosmic catastrophe known as the Big Rip. First, the expansion would tear apart galaxy clusters, then individual galaxies. As the force grows, it would shred stars from their solar systems, planets from their stars. In the final moments, even atoms and atomic nuclei would be torn asunder by the uncontrollable stretching of spacetime itself. The universe would end not in ice or fire, but in absolute disintegration. Pinpointing the exact value of W is therefore the central mission of 21st century cosmology. Current measurements from supernova, Baryon acoustic oscillations, and the cosmic microwave background all point to a value incredibly close to -1. But the uncertainty, the margin of error, is like a keyhole through which we can glimpse these extraordinary alternate futures. Is our universe destined for a steady expansion into a cold, dark emptiness, or a slow decay of the repulsive force, or a violent, ultimate dissolution? The answer lies in measuring this one number with ever greater precision, a task that demands a new generation of cosmic cartographers. But the simplicity of a single, constant number is also its greatest puzzle. Why should the energy of empty space have this exact, specific value? Theoretical calculations of the vacuum energy from quantum physics produce numbers that are unimaginably larger than what we observe, off by a factor of 1 followed by 120 zeros. This is the worst prediction in the history of science, a discrepancy so vast it suggests we are missing something fundamental. This deep unease has led physicists to explore a far more dynamic possibility. What if dark energy is not a static feature of the vacuum, but something that flows and changes? This alternative is known as quintessence, named for the fifth element of ancient philosophy, a substance beyond the ordinary earth, air, fire, and water. Quintessence proposes that dark energy is a field that permeates all of space, much like the Higgs field, but one that evolves over the lifetime of the cosmos. Unlike the rigid cosmological constant, a quintessence field can slowly shift its properties. Its energy density might have been much higher or lower in the distant past, and it could continue to change in the far future. This dynamism offers an elegant solution to a profound mystery called the cosmic coincidence problem. We seem to live in a very special moment, a cosmic blink of an eye where the energy density of matter and dark energy are roughly comparable. If dark energy were truly constant, this is an incredible accident. For most of cosmic history, matter was vastly dominant, and in the far future, dark energy will be overwhelmingly so. The fact that we exist precisely during this brief balancing act seems almost too fortunate. A quintessence field, however, could naturally explain this. Perhaps the field has been slowly weakening, and its current strength is not a permanent fixture but merely a phase we are passing through. Its energy density might be crossing that of matter now, not by chance, but as part of its intrinsic evolution. How could we possibly detect such a subtle shift in the fundamental fabric of reality? The answer lies in the detailed geometry of the cosmic web across time. If dark energy is a constant, its repulsive effect has been unchanging. The acceleration of the universe would have a specific, predictable signature on how the large-scale structure formed. But if dark energy is quintessence, its strength would have varied. This would leave a distinct imprint on the growth of galaxy clusters and the size of cosmic voids. A weakening quintessence field might have allowed structures to form more readily in the past than a constant dark energy would permit. By comparing the cosmic web from 8 billion years ago to the web of today, future telescopes could look for these subtle differences in the clustering of galaxies. It is like listening to a symphony played across billions of years. A cosmological constant would produce a single, steady note of acceleration. Quintessence would introduce a crescendo or a decrescendo, a change in the music of expansion that reveals a universe in flux. Phantom energy presents a universe that is fundamentally unstable, a cosmos where the very act of expansion fuels its own destruction. If the equation of state W were to slip below -1, dark energy would no longer be a passive background force. It would become an active, growing menace. The energy density would not remain constant as space stretches, it would intensify. Each new cubic centimeter of space created by expansion would contain more repulsive power than the one before, leading to an exponential feedback loop of acceleration. The consequence is the most violent endgame theorized by cosmology, the Big Rip. This would not be a slow fading into darkness. It would be a systematic and catastrophic unraveling of reality itself, dictated entirely by the geometry of dark energy. The timeline of this dissolution is calculated with chilling precision. First, the phantom energy's repulsive force would overcome the gravitational glue holding immense galaxy clusters together. These cosmic cities, each containing thousands of galaxies, would be flung apart. Next, the bonds within individual galaxies would fail. The Milky Way would be torn asunder, its stars scattered into the accelerating void. As the force grows stronger, it would target smaller and smaller structures. Solar systems would be the next to go, with planets ripped from their orbits around their parent stars. In the final hour, the destruction would become personal. The phantom energy's push would exceed the gravitational pull holding our planet together, and Earth itself would be explosively dismantled. In the last unimaginable moments, the forces binding atoms together, and even the strong nuclear force holding atomic nuclei intact, would be overwhelmed. Every piece of matter in the universe would be vaporized into a cloud of fundamental particles, isolated forever in an exponentially expanding emptiness. While this sounds like a plot from science fiction, it is a grimly logical outcome permitted by Einstein's equations of general relativity, provided this specific form of dark energy exists. Current data from cosmic surveys places the value of W incredibly close to -1, making a Big Rip scenario highly improbable. Yet, the tiny margin of error in our measurements means we cannot yet completely close the door on this cosmic doomsday. Its possibility serves as a powerful reminder that the geometry we are trying to map is not an abstract curiosity. It is the script for the final act of the universe, a story whose ending is still being written. This staggering mismatch is known as the cosmological constant problem, and it stands as the most embarrassing failure of theoretical prediction. Our most successful framework for understanding the subatomic world, quantum field theory, tells us that the vacuum of space should be a turbulent sea of energy. Even in complete darkness at a temperature of absolute zero, quantum mechanics dictates that virtual particles constantly flicker into and out of existence. This ceaseless activity should endow every tiny volume of space with a colossal energy density. When physicists calculate this amount, the number is unimaginably vast. It exceeds the observed value of dark energy by a factor of 1 followed by 120 zeros. To grasp the scale of this error, imagine predicting the distance to the moon and being off by the diameter of a single atom. It is a discrepancy so profound it suggests our fundamental tools for describing reality are either broken or profoundly incomplete. If the vacuum energy were truly as large as the quantum calculation suggests, the repulsive force would have been so immense that not a single star, planet, or atom could have ever formed. The universe would have blown itself apart in a fraction of a second after the Big Bang. The fact that we exist to ponder this question means the actual value is not just a little smaller, it is fine-tuned to an almost impossible degree of delicacy. This leads to an unsettling possibility. Perhaps there is some hidden symmetry or a yet unknown principle in physics that forces almost all of this vacuum energy to cancel out, leaving behind only a minuscule, non-zero remnant. This tiny leftover, a ghost of the theoretical storm, would be the dark energy we measure today. The alternative is that we are fundamentally misunderstanding the nature of the vacuum, and that its quantum energy does not gravitate in the way we assume. Either way, the cosmological constant problem is a glaring signpost pointing toward a revolution in physics, a hint that our map of reality is missing an entire continent of understanding. Perhaps the fine-tuning is not a puzzle to be solved, but a selection effect. This is the controversial path that string theory, a leading framework for a theory of everything, invites us to consider. String theory proposes that the fundamental constituents of reality are not point-like particles, but unimaginably tiny, vibrating strings. The specific resonance of these strings determines the properties of every particle and force. But for the mathematics to be consistent, string theory requires more than the 3 dimensions of space and 1 of time we experience. It suggests there are 6 or 7 extra spatial dimensions, curled up into a complex, microscopic shape called a Calabi-Yau manifold. The particular geometry of this manifold dictates the physical laws and constants of our universe, including the value of the vacuum energy. And here is the radical implication. There is not just one possible shape. The number of stable configurations for these extra dimensions is astronomically vast, perhaps as high as 10 to the power of 500. Each distinct configuration corresponds to a different universe with its own unique set of physical laws. This is the string theory landscape, a cosmic archipelago of possible realities. In the overwhelming majority of these universes, the vacuum energy is enormous. In such worlds, the repulsive force is so violent that space tears itself apart instantly, or matter is never able to coalesce into any structure whatsoever. These are dead universes, barren of stars, planets, or the possibility of life. Yet, within this near-infinite landscape, there will be an infinitesimally small number of universes where, by sheer chance, the convoluted geometry of the extra dimensions cancels out almost all of the vacuum energy, leaving behind the tiny, non-zero value we measure as dark energy. In this anthropic view, we do not live in a special universe, we live in a survivable one. The question shifts from why the constants are fine-tuned for life to why we find ourselves in a universe where life is possible at all. This explanation is deeply unsatisfying to many physicists. It feels like giving up on a fundamental explanation, trading a why for a where. It moves the goalposts from the laws of physics to the happenstance of our cosmic address. Yet, as a potential solution to the worst prediction in science, it forces us to confront the humbling possibility that our universe's habitability might not be a product of deep design, but a simple statistical necessity. Perhaps we are searching for a new ingredient in the dark when the real problem lies with the recipe itself. What if the accelerating expansion is not driven by a mysterious energy, but is instead a sign that our understanding of gravity is fundamentally incomplete? This is the provocative premise of modified gravity. For centuries, from Newton to Einstein, our theories of gravity have been resoundingly confirmed within our solar system and in binary star systems. But what if Einstein's general relativity, as beautiful and successful as it is, only tells part of the story? Perhaps it falters on the very largest scales, in the vast, near-empty reaches between galaxy clusters where the gravitational field is almost unimaginably feeble. In these cosmic deserts, the rules of attraction might subtly change. Theories like modified Newtonian dynamics, or MUND, propose that when gravity falls below a certain incredibly weak threshold, its behavior shifts. Instead of following the familiar inverse square law, its strength decays more slowly. On the scale of a single galaxy, this modification can explain the rotation of stars without requiring huge halos of dark matter. When extended to the cosmos, some versions of these theories claim the modified equations can produce an apparent acceleration of the universe's expansion, all without invoking a drop of dark energy. The appeal is immense. It offers a radical simplification, replacing two unknown entities, dark matter and dark energy, with a single adjustment to a well-known law. It suggests the universe is not dominated by mysterious, invisible stuff, but that we simply need a new set of glasses to see the familiar forces correctly. Yet, elegance alone is not enough. The challenge for any modified gravity theory is to pass every test that general relativity has already aced. It must account for the precise orbital dance of Mercury, the bending of light around the Sun, and the intricate timing of binary pulsars. More critically, it must explain the bulletproof evidence from the cosmic microwave background. The specific pattern of hot and cold spots in the infant universe is a fingerprint that tightly constrains the amount of normal matter and the total gravitational pull at work. So far, no modified gravity theory has successfully reproduced this detailed imprint without secretly reintroducing some form of dark matter. The recent detection of gravitational waves from colliding neutron stars delivered another crucial test. The waves and the light from the explosion arrived at Earth at virtually the same time, confirming that gravity travels at the speed of light, as general relativity predicts. Many simple modified gravity theories would have predicted a slight delay, a divergence that was not observed. This forces proponents to construct increasingly complex and fine-tuned versions of their models to fit all the data. The central tension remains stark. Is the universe filled with enigmatic components we cannot see, or are we witnessing the limits of our most cherished physical law? The answer will not come from philosophical preference, but from ever more precise maps of the cosmos, each new data point pressing down on the scales, weighing the soul of gravity itself. Yet this elegant synthesis now faces a serious challenge. A crack in the foundation of modern cosmology known as the Hubble Tension. The problem is deceptively simple. How fast is the universe expanding right now? We call this number the Hubble constant, a single value that should be universal. To measure it, scientists use two primary pathways. The first reads the baby picture of the cosmos, the cosmic microwave background. By analyzing the subtle patterns in this ancient light with incredible precision, the Planck satellite could extrapolate the universe's entire expansion history forward to today. predicting a specific, slower expansion rate. The second pathway is more direct. Astronomers look at stars and galaxies in our nearby universe. They use pulsating stars called Cepheid variables, whose intrinsic brightness is tied to their pulse rate, and type Ia supernova, our trusted standard candles. By measuring the distances and velocities of these objects, they calculate the current expansion rate directly. The unsettling result is that these two gold standard methods do not agree. The local universe measurements consistently give a faster, more rapid expansion rate than the prediction based on the early universe. This is not a small statistical fluke. As both sets of measurements have become exquisitely more precise, the gap between them has stubbornly remained, growing into a significant discrepancy. It is as if you calculated the final speed of a car based on its acceleration from a standing start, but when you actually clock its speed with a radar gun, the reading is noticeably higher. One of these methods must be missing something. Perhaps there is an unrecognized error in our measurement of cosmic distances, a subtle miscalibration in the ladder of standard candles. But as checks and rechecks confirm the results, a more thrilling possibility gains weight. This tension might not be a mistake at all, but a signal. It could be the first observational clue that dark energy is not the simple, constant force we have assumed. What if the properties of dark energy underwent a slight shift, a gentle evolution after the era of the cosmic microwave background? A dynamic dark energy that was a fraction weaker in the past could have allowed the universe to expand just a bit more slowly initially, matching the CMB data, before strengthening to produce the faster expansion rate we see today. This would resolve the tension elegantly, but at the cost of discarding the beautifully simple cosmological constant. The Hubble tension, therefore, is more than a technical disagreement. It is a potential window into the evolving nature of cosmic repulsion, a hint that the geometry of dark energy may hold dynamic secrets we are only beginning to perceive. This cosmic tension demands a new kind of eye, one capable of surveying the heavens with a breadth and speed previously unimaginable. The Nancy Grace Roman Space Telescope is that instrument, an observatory designed from the ground up to be a dark energy discovery machine. Its most powerful asset is a field of view 100 times larger than the Hubble Space Telescope's infrared camera. While Hubble is a brilliant detective, peering intently at a single cosmic clue for days, Roman will be a master surveyor, mapping the entire sky with a sweeping gaze. It will not just take pictures, it will capture the dynamics of the cosmos in motion. Over its mission, Roman is set to conduct monumental surveys, gathering more data in its first few months than Hubble has collected in its entire decades-long lifetime. It will measure the distances to thousands of type Ia supernova, tracing the expansion history with a richer, more detailed timeline. It will map the positions of millions of galaxies to pinpoint the Baryon acoustic oscillation standard ruler with exquisite sharpness, seeing how its apparent size has changed across billions of years. And with its incredibly sharp vision, it will observe the subtle, weak gravitational lensing distortions in the shapes of billions of galaxies, creating the most precise three-dimensional mass map of the universe ever assembled. This trifecta of measurements, all from a single powerful mission, will allow scientists to triangulate on the equation of state parameter W with a precision that borders on the microscopic. Current data tells us W is very close to -1, but is it exactly -1, locked in place for all eternity like a cosmological constant, or does it waver by a fraction of a percent? Roman's vast dataset will shrink the margin of error so dramatically that it could detect the faintest whisper of a deviation. That tiny signal would be everything. It would be the first definitive evidence that dark energy is not a static property of space, but something dynamic, a quintessence field slowly changing over cosmic time. The mission will essentially provide a high-definition movie of the universe's expansion, frame by precise frame, allowing us to watch the tug-of-war between gravity and dark energy play out across the eons. It is the next great step in moving from a snapshot of cosmic geometry to a living, breathing portrait. While Roman scans from the tranquility of space, a relentless new eye will open on Earth. Perched high in the dry Chilean mountains, the Vera Sea, Rubin Observatory is an instrument of pure cosmic ambition. Its mission is the legacy survey of space and time, a 10-year project of almost unimaginable scope. Imagine a camera so powerful it can capture a patch of sky containing thousands of galaxies in a single exposure. Now imagine that camera pivoting night after night, systematically photographing the entire visible southern sky every few nights. This is not a static map, but a high frame rate movie of the universe. Over a decade, the survey will catalog billions of galaxies and witness the flare of millions of supernovae, creating a living, breathing atlas of the cosmos. The sheer torrent of data will be staggering, but within that flood lies the potential to see dark energy in motion. The LSST will track how the cosmic web evolves not over billions of years, but almost in real time. By measuring how the clustering of galaxies subtly shifts from one year to the next, astronomers can detect the accelerating stretch of space with a fresh, dynamic precision. The survey will also perform weak gravitational lensing on an industrial scale. By analyzing the tiny distortions in the shapes of billions of galaxies, it will trace the distribution of dark matter with a statistical power so immense it can reveal the faintest whispers of dark energy's influence on the growth of structure. The true power, however, lies in the synergy, the Nancy Grace Roman Space Telescope with its exquisitely sharp vision from above the atmosphere, and the Vera Sea. Rubin Observatory, with its wide field and relentless pace from the ground, will form an unbeatable partnership. They will cross-check each other's findings, using different techniques to corner the same quarry. Roman might measure the precise distance to a supernova, while Rubin provides the context of its surrounding galactic neighborhood. Together, they will leave dark energy with fewer places to hide, tightening the constraints on its nature from every possible angle. This dual assault represents a new era of observational cosmology, where we no longer just look at the universe, we watch it live. This multi-pronged assault on the unknown requires a new generation of cosmic cartographers, each with a unique specialty. The European Space Agency's Euclid Mission is already in space, its sole purpose to map the invisible architecture of the dark universe. Euclid is an entirely different kind of observer, designed not for stunning deep-field images but for immense, precise statistical power. It will spend its mission surveying an enormous portion of the sky, meticulously measuring the shapes and precise distances of over 1 billion galaxies. This colossal dataset will allow it to perform weak gravitational lensing measurements with a level of detail that dwarfs previous efforts, tracing the distribution of dark matter with unprecedented fidelity. Simultaneously, by pinpointing the positions of so many galaxies, it will measure the Baryon acoustic oscillations standard ruler across a vast range of cosmic time, creating a high-definition movie of the universe's expansion history. Euclid's strength is in its sheer scale, its ability to see the grand pattern of the cosmic web in breathtaking detail. While Euclid maps the large-scale structure, the James Webb Space Telescope acts as a cosmic time machine peering into the deepest past. Webb's incredible sensitivity to infrared light is its superpower. The expansion of the universe stretches the light from the most distant objects into the infrared part of the spectrum, and Webb is built to capture that faint, ancient glow with unparalleled clarity. It is looking back to the era of the very first galaxies, observing the infant cosmic web when it was just beginning to form. By studying these primordial structures, Webb provides a crucial baseline. It helps astronomers understand the initial conditions of the universe, calibrating our models for how gravity alone should have built the cosmos over time. This allows us to isolate dark energy's specific effect, its relatively recent influence in opposing that growth. Furthermore, Webb's sharp eye is observing distant Type Ia supernova with a precision never before possible, refining our cosmic distance ladder and providing an independent, highly accurate check on the expansion rate in the early universe. This is the power of a multi-wavelength strategy. Each telescope sees the cosmos through a different lens. Euclid sees the grand statistical tapestry. Webb sees the fine, ancient details. The Nancy Grace Roman Space Telescope will provide the expansive, dynamic view. Together, they form an interconnected network of observation, a system of checks and balances that is essential for rooting out subtle errors. An anomaly seen by one instrument can be confirmed or refuted by another. A measurement made in visible light by Euclid can be cross-referenced with an infrared observation from Webb. This collaborative approach minimizes the risk of systematic biases, those tricky instrumental or methodological errors that can lead us astray. By triangulating on dark energy from every possible angle with different tools and different techniques, these observatories are not just looking for an answer. They are building an irrefutable case, ensuring that whatever we discover, whether it is a constant or a dynamic field, is a true feature of the universe and not a phantom in the data. The geometry of dark energy is being traced by a chorus of voices, each singing a different part of the same cosmic song. But to peer into the deepest cosmic epochs, we must learn to see in a different kind of light. The next frontier of cosmic cartography listens to the universe rather than simply looking at it. It tunes its instruments to a faint, specific radio whisper emitted by the most abundant substance in the cosmos, neutral hydrogen gas. This whisper has a precise signature, a wavelength of 21 centimeters, and it holds the key to a movie of the universe spanning billions of years. Giant radio telescope arrays like the Planned Square Kilometer Array, or SKA, are designed to be the ultimate ears for this cosmic broadcast. Instead of a single dish, the SKA will consist of thousands of radio antennas spread across vast distances in South Africa and Australia, working in concert to create a single, colossal virtual telescope with a collecting area of, as the name implies, a square kilometer. Its sensitivity will be unparalleled. This network will scan the heavens not for the light of stars, but for the faint radio hum of diffuse hydrogen gas that fills the immense voids between galaxies. This gas is the true backbone of the cosmic web, a relic from the primordial universe. By detecting the subtle redshift of this 21-centimeter line from hydrogen at different distances, the SKA can construct a three-dimensional map of the universe on a scale that is almost unimaginable. It will chart the distribution of matter not just by pinpointing bright galaxies, but by tracing the invisible hydrogen that constitutes the vast majority of ordinary matter in the cosmos. The true power of this technique lies in its reach through time. It can map the structure of the universe from a period known as the Cosmic Dark Ages, before the first stars ignited, all the way to the present day. This would provide a continuous, direct film of how the cosmic web has evolved. We could watch gravity slowly pull matter into filaments and nodes, and then witness the precise moment when dark energy's influence began to put the brakes on this growth. By comparing the clustering of matter at different epochs in this grand timeline, scientists could measure the properties of dark energy with a precision that is completely independent of supernova or the cosmic microwave background. It is a direct measurement of the geometry of space as it has stretched over time, offering a clean, powerful test that could finally tell us if dark energy is truly constant or if its fingerprint changes across the eons. This is not just another observation, it is a new way of seeing, a shift from cosmic photography to a full-length feature film of the universe's evolution. The cosmic maps from telescopes like Euclid and the Vera Rubin Observatory are not simple pictures to read. They are vast, encrypted records of a struggle that has played out over billions of years. To decipher them, cosmologists must build their own universes from scratch. This is the realm of supercomputers, where the theoretical meets the tangible in colossal simulations. These are not video games but digital laboratories of immense complexity, designed to test our ideas about dark energy against the hard evidence of the real cosmos. The process begins with a set of initial conditions, a recipe based on the precise measurements from the cosmic microwave background. Scientists define the ingredients, the amounts of dark matter, normal matter, and crucially, the properties of dark energy they wish to test. Is it a constant cosmological constant, or a dynamic quintessence field with a specific rate of change? Each assumption becomes a different virtual universe. Into this primordial digital soup, the supercomputer introduces billions, even trillions, of virtual particles representing dark matter. The laws of physics are programmed in, primarily the relentless pull of gravity. Then the simulation begins. Over millions of processor hours, the computer calculates the gravitational dance of every particle, modeling the evolution of the universe from its infancy to the present day. You watch as gravity works its magic, pulling the dark matter particles into a cosmic web of filaments and nodes. Gas follows the gravitational potential of the dark matter, cooling and collapsing to form virtual galaxies. The entire history of structure formation unfolds inside the machine. The true test comes when the simulation is complete. Scientists do not just look at a pretty animation. They perform the exact same statistical analyses on the virtual universe that they do on the real one. They measure the clustering of the simulated galaxies, the sizes of the voids, and the subtle distortions of weak gravitational lensing within the digital cosmos. They generate a simulated cosmic map. Then comes the critical comparison. They place this digital map next to the one painstakingly compiled by the Dark Energy Survey, or soon from the Nancy Grace Roman Space Telescope. Does the virtual universe, with its specific model of dark energy, produce a cosmic web that matches the geometry of our own? If the patterns align, the statistical fingerprints of galaxy clustering and lensing match, it is a powerful vote of confidence for that particular dark energy model. If they disagree, if the voids are the wrong size or the filaments too clumpy, that model is ruled out. These simulations are the essential bridge between raw data and profound understanding. They allow us to run experiments that are impossible in the real world, tweaking the fundamental laws to see which version of reality best fits the grand, geometric pattern we see etched across the sky. This overwhelming cosmic inventory forces a profound shift in perspective. We are not the center of the universe in any material sense. The very substance of our being, the atoms that form stars, planets, and life itself, is a mere afterthought in the cosmic ledger, a tiny 5% flavoring in a sea of darkness. The forces that truly govern the cosmos are utterly alien to our daily reality. We live our lives governed by gravity's familiar pull and the solidity of matter, yet these are not the dominant players on the universal stage. The true architects are invisible, their natures completely unknown. This realization is a form of cosmic humility, a reminder that our perception of reality is constructed from a narrow slice of the full spectrum of existence. We are like deep-sea creatures who have only ever known the crushing pressure and absolute darkness of the abyss, suddenly granted a glimpse of the sunlit surface world. Our entire frame of reference is local, limited, and perhaps even provincial. The universe, it seems, is not designed for our comprehension. It operates on rules that are, for now, written in a language we cannot decipher. This brings us to an even deeper mystery, one that borders on the metaphysical. The value of dark energy's strength appears to be exquisitely, almost impossibly, fine-tuned. If the cosmological constant were only slightly larger, the repulsive force would have been so powerful in the universe's youth that it would have ripped apart the primordial clouds of gas before they could ever collapse into the first stars. No stars mean no planets, and certainly no life. We are here only because the dial controlling this cosmic repulsion was set to an incredibly precise and seemingly arbitrary value. This apparent fine-tuning screams for an explanation. Is it merely a monumental coincidence, a one-in-a-trillion chance that we happen to inhabit the one universe where the number's just right? Or does it point to a deeper principle, a law of physics we have yet to uncover that mandates this specific value? The more unsettling possibility, as we have seen, is the anthropic principle, the idea that our universe is just one among a near-infinite multitude in a vast multiverse. In this cosmic lottery, most universes are stillborn, their physical laws incompatible with complexity or life. We, of course, can only find ourselves in a universe that permits our existence. The fine-tuning is not a sign of design, but a consequence of our own point of view, a selection bias on a cosmic scale. This idea is deeply unsatisfying to many, as it seems to halt the search for a fundamental reason. Yet it forces us to confront a humbling question. Are the laws of physics we hold as universal truths merely the local bylaws of our particular cosmic neighborhood? The geometry of dark energy, then, is more than a physical map. It is a mirror reflecting our own profound ignorance and challenging our most basic assumptions about reality, causality, and our place in the grand scheme of things. This accelerating future may have a profound echo in the distant past. The universe has experienced a period of runaway expansion before. In the very first sliver of a second after the Big Bang, a phenomenon called inflation took hold. During this unimaginably brief epoch, the cosmos swelled exponentially, stretching from a subatomic speck to something macroscopic in a time span so short it defies analogy. This violent growth spurt served a critical purpose, ironing out any wrinkles in the fabric of space and transforming microscopic quantum jitters into the faint density variations that would later blossom into galaxies and cosmic voids. The engine for this explosive event was not dark energy, but a hypothetical field known as the inflaton. Yet when physicists write down the equations for inflation, they bear a striking and suggestive resemblance to the equations we use for dark energy. Both describe a universe dominated by a form of energy that causes space to stretch at an accelerating rate. This mathematical kinship is too compelling to ignore. It raises the tantalizing possibility that dark energy is a faint, lingering whisper of the same kind of physics that orchestrated the universe's birth. Perhaps the inflaton field did not vanish completely but decayed into a much weaker counterpart that has lain dormant for billions of years, only now reasserting itself as dark energy. If this connection is real, then the key to understanding the ultimate fate of the cosmos might be locked in the physics of its first moment. By studying the subtle properties of dark energy today with our powerful new telescopes, we could be gathering clues about the inflationary epoch. The precise value of the equation of state, the parameter W, might tell us something fundamental about the nature of the inflaton field itself. Solving the mystery of why the universe is flying apart now could inadvertently illuminate the mystery of how it began. This would weave a single, continuous thread from the fiery genesis of everything to its cold, final state, creating a unified story of cosmic evolution from beginning to end. Based on our best measurements, the most probable future for our cosmos is a slow, silent fade into a perpetual icy darkness. This is the heat death, or big freeze, a conclusion dictated by the steady, unchanging push of a cosmological constant. In this timeline, dark energy's influence only grows as the universe continues to expand and thin out. The galaxies beyond our immediate gravitational family, the local group, will one day cross a cosmic horizon. Their light, stretched to wavelengths longer than the universe itself, will simply cease to arrive. The sky, for any future astronomers, will go dark, the evidence of an expanding cosmos vanishing from view. Over trillions upon trillions of years, the last stars will flicker out, their fuel exhausted. Eventually, even the black holes, those cosmic anchors, will radiate away their mass in a final whisper of Hawking radiation. The universe will become a vast, ever-cooling sea of isolated particles, a dilute and featureless void where time itself may lose all meaning. This is the future if dark energy is truly constant. Yet the geometry we are trying to measure holds the pen that will write this final sentence. A dynamic dark energy, a form of quintessence that weakens over time, could lead to a different ending. The acceleration might gradually slow, perhaps even allowing gravity a final, feeble chance to pull on the cosmic fabric, though the universe would likely still expand forever, just at a more leisurely pace. But if the phantom energy scenario is correct, the finale is not a quiet fade but a violent, explosive end. The very fabric of spacetime would tear itself apart in the Big Rip, a final, catastrophic act of disintegration. The choice between an eternal ice age, a gradual slowdown, or a sudden shredding of reality hinges entirely on the precise, unseen geometry of the force we call dark energy. Mapping its hidden structure is not an abstract exercise. It is an act of reading our ultimate destiny written into the stretching sky. This quest for precision forces us to confront the limits of our own vision. Every measurement in cosmology is a battle against subtle, insistent errors that can quietly twist our view of reality. These are not simple mistakes, but systematic biases woven into the very process of observation. Imagine trying to measure the growth of a tree over a century using a camera whose lens slowly warps with age. The tree might appear to be stretching in a way that has nothing to do with its actual growth. This is the nature of systematic error. For a ground-based telescope, Earth's atmosphere is a shimmering, turbulent lens that subtly smears the shapes of distant galaxies, potentially faking the weak lensing signal we attribute to dark matter. The camera itself might have tiny, almost imperceptible flaws in its sensors that cause it to misread the brightness of a crucial supernova. Even our own analysis software, the algorithms we write to find patterns in the data, can introduce their own biases, seeing a signal that we programmed it to find. The only defense is a strategy of overwhelming redundancy. By using different telescopes on the ground and in space, by applying multiple independent analysis techniques to the same dataset, and by constantly cross-checking results, scientists can slowly isolate these systematic gremlins and subtract their influence from the true cosmic signal. Beyond the flaws in our tools lies a more profound and existential limitation, the problem of cosmic variance. We are, by definition, trapped inside a single universe. We can only ever observe the one cosmic volume that is accessible to our telescopes. A finite sphere limited by the distance light has traveled since the Big Bang. This is our observable universe, but is this volume a fair sample of the whole? What if, on scales larger than we can ever see, the density of galaxies or the strength of dark energy is slightly different? It is like trying to understand the global climate by only ever measuring the weather in your own backyard. Your data might be perfectly precise, but it could be completely unrepresentative. This cosmic variance sets a fundamental, unbreakable ceiling on the precision of our measurements. No matter how good our telescopes become, we can never know for certain if the large-scale structure we see is truly typical or just a statistical fluke of our particular cosmic neighborhood. This is why the next generation of surveys are so vast. By mapping an enormous volume of space containing billions of galaxies, they effectively average over many smaller subregions, reducing the uncertainty imposed by our single, unique point of view. The ultimate map of dark energy is therefore a masterpiece of error correction, a picture painstakingly cleaned of instrumental distortion and statistically weighted against the chance that we are simply living in a strange part of the cosmos. The sheer scale of this cosmic cartography presents a monumental challenge. To map dark energy, we need to classify the shapes of not thousands, but billions of galaxies, a task far too vast for any single team of astronomers to accomplish alone. This is where the search for the universe's hidden geometry becomes a truly human endeavor, embracing the power of citizen science. On platforms like Zooniverse, anyone with an internet connection can contribute to groundbreaking research. Volunteers from all walks of life log on to examine real images captured by telescopes like Hubble, visually inspecting distant galaxies to classify their forms. Is a galaxy a neat, swirling spiral or a smooth, featureless ellipse? This simple act of classification is not just busy work, it is the essential first step for the weak gravitational lensing studies that trace the distribution of dark matter. The human brain possesses an extraordinary and still unmatched capacity for pattern recognition. While computer algorithms are powerful, they can be confused by the messy realities of the cosmos, like galaxies that are overlapping, oddly shaped, or warped by gravitational lensing itself. The intuitive glance of a human volunteer can spot these anomalies, providing a crucial layer of quality control that trains and refines the very algorithms used by scientists. By participating, people around the world become active participants in the scientific process, their collective effort forming a global network of cosmic cartographers. Each galaxy classified is another data point in the grand map, another stitch in the tapestry of the cosmic web. This collaborative effort transforms an abstract scientific quest into a shared human experience, directly connecting individuals to the profound mystery of dark energy and our place in a universe whose final shape is still being drawn. The same digital tools that sift through billions of galaxies for signs of cosmic distortion are now helping radiologists detect subtle patterns in medical scans, identifying early signs of disease with a precision that was once impossible. This cross-pollination of technology is a direct result of the immense challenges posed by dark energy. To build a map of the invisible, we first had to build a new generation of eyes. The camera at the heart of the Vera Rubin Observatory, for instance, is not just large, it is a masterpiece of optical engineering with a resolution of over 3 billion pixels. The quest to capture the faint, distorted shapes of distant galaxies demanded sensors of unparalleled sensitivity and stability, pushing the limits of materials science and electronics. These advancements in imaging technology do not stay locked in an observatory dome, they ripple outward. The algorithms developed to clean atmospheric turbulence from telescopic images are now refining satellite imagery for environmental monitoring and urban planning. More profoundly, the entire field of cosmology has been forced to become a world leader in handling big data. A single night of observation with these new telescopes can generate terabytes of information, a flood of raw data that would be meaningless without sophisticated software to process it. Cosmologists had to pioneer new methods in machine learning and artificial intelligence to classify galaxies, measure their shapes, and find the subtle statistical signals buried in the noise. These are not minor tweaks to existing code. They are fundamental advances in pattern recognition and data analysis. The techniques created to find the frozen sound waves of Baryon acoustic oscillations in a galactic map are now being adapted to analyze complex financial markets or model the spread of information across global networks. The drive to understand the cosmos, a pursuit that seems so abstract and distant, consistently forces breakthroughs in practical computation that eventually touch nearly every aspect of modern life. This is the hidden return on investment for fundamental science. We set out to answer the biggest questions about the nature of reality, and along the way, we inevitably develop the tools to improve our own world. The search for dark energy is not just a journey outward, it is an engine for innovation here on Earth. Decades of observation have confirmed the reality of dark energy, yet its essence remains locked in shadow. We can chart its influence on cosmic expansion with breathtaking precision, and our theoretical models provide elegant containers for its behavior. But the fundamental question of what it is remains one of the greatest unsolved puzzles in all of science. Is the cosmological constant the final answer, a simple number etched into the fabric of reality? Or are we witnessing the slow evolution of a quintessence field, a dynamic force with a history of its own? Perhaps the most radical possibility is that dark energy is not an energy at all, but a glaring sign that Einstein's theory of gravity, while brilliant, is an incomplete picture that fractures on the largest scales. The flood of data from observatories like the Roman telescope and the Vera Rubin Observatory will ruthlessly narrow these options, ruling out entire families of theories. Yet there is no guarantee that the result will be a neat solution. The history of cosmology suggests that deeper answers often lead to more profound questions. The true revelation might be a phenomenon we have not yet even dreamed of, a new layer of cosmic weirdness that challenges our understanding of physics at its most fundamental level. This investigation forces a humbling acknowledgement. We are pushing against the very boundaries of knowledge, staring into a darkness that is not empty but filled with possibility. The universe, in its infinite complexity, continues to defy our attempts at a simple explanation, reminding us that the greatest discoveries often lie not in the answers we find, but in the new mysteries they unveil. This staggering mismatch between quantum prediction and cosmic observation is more than an embarrassment, it is a fundamental crisis. It points to a chasm in our understanding of reality so deep that it may require a revolution in physics to bridge. We have two incredibly successful theories, each a masterpiece in its own domain. General relativity describes the cosmos on its grandest scales, the graceful dance of planets and the warping of spacetime by galaxies. Quantum mechanics governs the bizarre and probabilistic world of the atom. The problem is, these two rulebooks are written in completely different languages, and they contradict each other. General relativity paints a smooth, continuous fabric of spacetime, while quantum mechanics insists that at its heart, everything is granular and jittery. When we try to apply the rules of quantum mechanics to the fabric of spacetime itself, to create a theory of quantum gravity, the mathematics breaks down into nonsensical infinities. This is the core of the cosmological constant problem. Our quantum calculation of vacuum energy treats spacetime as a fixed, static stage, but general relativity tells us the stage itself is dynamic, bending and stretching. We are trying to calculate the energy of the actors without understanding that the floorboards are part of the play. A true theory of quantum gravity would describe how space-time behaves at the most fundamental level, at the unimaginably tiny Planck scale. It would tell us what empty space truly is. Is it a seething foam of wormholes and tunnels, as some models suggest? Is it woven from tiny, discrete loops, as proposed by loop quantum gravity? Or is it built from vibrating strings, as string theory posits? In such a theory, the concept of vacuum energy might be completely transformed. Perhaps the frantic quantum activity of virtual particles does not gravitate in the simple way we assume. Maybe the true nature of quantum gravity involves a subtle cancellation or a topological property that naturally leads to the tiny, non-zero value we observe. The quest to understand dark energy, therefore, is inextricably linked to the holy grail of modern physics. We are not just measuring an acceleration, we are probing the quantum structure of spacetime. The solution to the dark energy puzzle may not be found by simply staring deeper into the cosmos with bigger telescopes, but by finally uncovering the unified laws that govern both the very small and the very large, revealing why our universe has the specific, life-permitting geometry that it does. Our journey to map the unseen geometry of dark energy is a profound reflection of our own curiosity. It began with a cosmic surprise that overturned centuries of understanding and led us to a universe dominated by a force we cannot see. We have followed the trail from Einstein's discarded constant to the vast digital sky surveys that trace the cosmic web, using frozen sound waves and the bending of light as our guides. We have weighed the possibilities from a dynamic quintessence field to a radical rewriting of gravity itself. For now, the simplest answer, a cosmological constant etched into the vacuum of space, remains the best fit to the mountain of data we have collected. Yet the universe whispers that the story may not be so simple. The persistent Hubble tension is a quiet but insistent clue that our map might be missing a crucial feature, a subtle evolution in the dark energy that has yet to be fully revealed. The next decade will be a golden age of cosmic cartography. The Nancy Grace Roman Space Telescope, the Vera Rubin Observatory, and the Euclid Mission are not just new instruments, they are a new way of seeing. Together, they will produce a living, breathing portrait of the universe's expansion, measuring its every nuance with a precision that borders on the absolute. They will shrink the margins of error around our theories until the true nature of dark energy is cornered by evidence. This quest is far more than a technical challenge for astronomers. It is a fundamental chapter in the human story, a continuation of our ancient need to look up at the night sky and comprehend the forces that govern our existence. To understand dark energy is to read the final pages of our cosmic destiny, written in the hidden geometry of everything. The map is still being drawn, and the final picture, whatever it reveals, promises to reshape our place in the cosmos.